Hello everyone, and welcome to the seventh topic in the SS2 Physics First Term curriculum. Now, in this topic, we'll be looking at equilibriums of bodies in liquid. Now, before we go into this, I'll advise that if you haven't checked out the videos so far, please ensure that you do so, especially what we did in week 6, where we discussed equilibrium of forces. So because that serves as a precursor to what we're about to do in this topic, because this time we are looking at equilibrium of bodies, but when they are in a liquid is what we are focused on at this point in time. And of course, if you don't already know, this is Oya Learn, our channel where we bring you helpful educational materials like this that help you get better in your academic life. So please, if you're not subscribed to the channel, kindly take a moment of your time, click the subscribe button, and one thing that can also help is when you hit the notification bell icon. Now, what that does is that every time we put out a new video, you will always be notified of it. And please help us to reach many more students like you who need the kind of helpful content that we are doing here on this channel. And how you can help us do this is by sharing the video. So kindly click the share button and don't forget to leave us a comment. If there's something you would like us to do or if there's an explanation you would like from us, please put your questions in the comment sections of the videos and we'll definitely attend to all of your comments. Now, to what we have for week 7 here, this is equilibrium of bodies in liquid. Now, the things that we're going to cover in this topic are listed here. You know that whenever, it's a common experience, whenever you are in water, when you go swimming, you feel lighter. Now, what explains that to us is one of the things we're going to look at in this topic when we study what is known as the Archimedes principle. Now, we'll look at what the principle itself states, and then we give a practical explanation to what the principle is trying to explain, so that you get a full understanding of the principle and how it is applied in our day-to-day life. Now, after that, we'll also look at what is known as the principle of flotation. Now, many students often mix that up. They think Archimedes' principle is the same thing as the principle of flotation. Now, we can say that yes, they are connected, they are related to each other, but they are two different principles. In this case, this one is telling you, Archimedes' principle is telling you what happens when an object is partially or completely immersed in a fluid. But the principle of flotation is telling you the conditions that will make that object that is immersed in a fluid to float. So if a person is in water, will the person float or will the person sink? If you throw a particular material in water, will it float or will it sink? What if it's a different kind of liquid entirely? Will it float or sink? That is what this principle is telling us about. By the time you go through this principle, you'll be able to understand why is it that metal boats are able to float on water. Why is it that a very heavy ship is able to float on water? All of this you would understand by the time we talk about the principle of flotation. Now, after that, we also dive into density and relative density. We'll be able to define what density is and then what relative density is and then how it is applied in physics. And then we go to the measurements of density and relative density. Now, for those of you who are preparing for exams of different kinds, there are a lot of questions you will get on density and relative density, especially with the measurements. So we would explain how you measure the density of objects that will sink in water, especially solids. We look at how you measure the same thing for objects that will float in water or other liquids. We also look at how you can measure the density of particles that are in material solids that are in particle form, say like sand and things like that. How do you measure their density? We also look at how you measure the density of materials that will dissolve in water, that is, they are water soluble. Then how can you find the density of such kind of materials? We'll also discuss that at that stage. And then we'll also look at how you can measure the density of other liquids. And once you know how to measure the density, we'll also discuss how to find the relative density of same material. Now, at this stage, you'll be solving a lot of questions from the WAEC curriculum, from the JAM curriculum, and other kinds of professional exams. We'll look at how to solve those kind of questions, and you will really need to pay attention at that point because I'll be giving you a lot of tips that will help you solve questions like that without error all the time. And then to close the topic, we'll then look at the hydrometer. Now, this is an instrument. I will look at what it looks like and what it is used to do. We'll also answer a few questions on hydrometer, those kind of common questions that you find in multiple choice exams, especially on this topic, which is the equilibrium of bodies in liquid. So that's about what we're going to be covering in this video. So you see, you do not want to miss any part of it. So please get relaxed as we dive into the world of equilibrium of bodies in liquid. Have you ever heard the term take a load off? Now, you see that term take a load off refers to you relaxing. Perhaps when you are worked up, you've done a lot of stressful activity and you need to relax, you'll be told, take a load off. Now, you see, in physics, this term can be quite literal when we consider the Archimedes principle. Now, for example, one thing I love to do when I'm stressed is go for a swim. Or sometimes I just go home and then dunk myself in the bath and just sit there in the water relaxing. It is really literal when I say I am relaxing or taking a load off when I sit in that bathtub that is filled with water. I am actually taking a load off. Now, let's see what this actually means when we consider what is known as the Archimedes principle. Now, this principle states that when an object is partially or completely immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced. Let's put that down. Archimedes' principle states that when an object is partially or completely immersed in a fluid, it experiences an upthrust, which is equal to the volume of the fluid displaced. Now, what does this principle mean? Now, you can try this and tie a string to a particular bucket, small, and then dip it into a liquid, say water, for example. Now, you experience that the moment it is partially or completely immersed in that fluid, that particular weight that you feel on the end of the string becomes lighter. But the moment you pull it back out of the water, it becomes heavier again. Now, what actually happened in the fluid? Let's say this is the bucket of water. You have a small bucket and then there's a fluid here. Now, what happens the moment it gets into the water? Now, by the time it is immersed in the fluid, you are supposed to feel a tension in the string. There's a tension in the string, which is the weight of what you are holding. But the moment it is in the water gives it an upward force. Now, you see, this upward force is what is known as upthrust. It's kind of like a cushioning effect, relieving the load that you feel when you dip it in water. So you see what I meant when I said taking a load off could be literal in physics. Because the moment you are dunked in water, the water gives you that little bit of push from under that relieves you. It takes a weight off of you. You don't feel your full weight anymore when you are in that water. That's why I say it is literal. You are actually taking a load off. Now, this depends on a number of factors. We have to consider first the volume of the fluid that is displaced. That is, when you dip it in that water, how much water will be pushed away from you the moment you dip it in that water. Then secondly, you have to consider acceleration due to gravity at that point. And then with that also, you have to consider viscosity of the fluid, amongst other things. But those that really come out there are the gravitational acceleration and the volume of the fluid displaced. Now let us look at how all of these come together so that we can see how much load is actually taken off a material that is partially or completely immersed in fluid. But before we end this, don't forget, if you are asked to state the Archimedes principle, all you need to say is, it states that when an object is partially or completely immersed in a fluid, it experiences an upthrust. This upthrust is the weight that is taken off that material. It's a weight loss, which is equal to the volume of the fluid displaced. So you too can take a load off just like Archimedes did. When you dip an object in a fluid, say water for example, by Archimedes' principle, we now understand why it feels lighter. And that is because it receives a cushioning effect from that water or whichever fluid you are using in your own case. And that cushioning effect is what is known as upthrust force. That is why the principle said when it is partially and completely immersed in a fluid, it experiences an upthrust. Now, how can you calculate for that upthrust force? That is, what are the factors that tells us the value of the upthrust force that is felt when you partially or completely immerse an object in a fluid? Now, to calculate upthrust force equal the product of volume of the object will be multiplied by the density of the fluid since I'm using water, I'll say density of water, and then we multiply that by acceleration due to gravity. Acceleration due to gravity. Now, these are the three things that gives us the value of the upthrust force. Okay? Once again, volume of the object multiplied by the density of the water multiplied by acceleration due to gravity. Now, how do we denote all of this? The upthrust force can be denoted U or sometimes P or U. And this equals, I'll be using U since we are using upthrust. So U equals volume of the liquid, volume of the object rather, that will be V, multiplied by density. Density is denoted with this symbol. And then we multiply that by acceleration due to gravity. So this is what we are using. Okay. Now, remember, from the principle we said when the object is partially or completely immersed. This will be a case when the entire volume is dunked into the water. But when the entire volume is not, you have to look at the fraction that is immersed. Okay? So when it is partially immersed, what you now do is the upthrust felt becomes the fraction of volume that is immersed. Then you multiply that by the density of water multiplied by acceleration due to gravity. Now, I must mention, I've been saying this for a lot of our videos now, that when it comes to using acceleration due to gravity, in most cases, you'll be given a value to use. And sometimes it could be given as 10.0, right? But when it is not given, it's always safe to use values that are closer to 10, say like from 9.87 and so on. 9.87 is the agreed value, constant that we can use for acceleration due to gravity. However, most times when we solve problems like this, we tend to use a round figure so that it makes it easy on our calculation. That is why we use 10 a lot. Okay, so always look out for the acceleration due to gravity that is given in the question that you are trying to solve. But when it is not given, you can always state applying acceleration due to gravity equals, then state the value you want to use, 9.87, or you can also use 10.0 meters per second square. As long as you state it, you are in the safe zone for solving that kind of a question. So now we know Archimedes' principle. we can state it, and we can even write the equation for it. Let's apply this equation now to solve whether the upthrust, the volume of the liquid itself. We can even find the mass of the liquid. We can even use it to find acceleration due to gravity at that point. Let's apply it to solve some questions from WAEC, JAM, and so on, so that we learn how to use this equation without failure. Let us practice how to solve for upthrust by using this question. The question says an object of volume 6.67 times 10 raised to the power minus 3 meter cubed, when suspended from a spring balance, is lowered into a liquid of density 0.9 grams per cm cube until 2/3 of its volume is immersed in the liquid. Calculate the weight that would be measured by the spring balance. Now we know that the weight that will be measured by the spring balance is the original weight of the material minus the upthrust that is felt. So we have to first calculate for the upthrust before we can get the weight that will be measured by the spring balance. And we are given some hints where gravitational acceleration is 10 meters per second cubed and the mass of the object in air is 100 grams. Now let's use this to calculate for the weight that will be measured by the spring balance. Now, before we can go on to calculate, there are some things we need to tidy up first. You see here that the density of the liquid is not given in the proper SI unit. So we have to convert this to kilogram per meter cubed. Okay? Then another thing we have to work on is, you see this mass, we need to convert it to weight. That is, take it to Newton. So, and this is in grams, so we have to bring it to kilogram and then to Newton. So let's see how we do that. So let's solve that part on this place, at this part of the board here. So here will be our solution. Starting with the density. The density is 0.9 gram per cm cubed, which is basically, now 0.9 gram is 0.9 over 1000 to bring it to kilogram. Okay? Now, divide that by the 1 cm cube. 1 centimeter is 1 over 100, bringing it to meter. Now you have to cube this. Okay? Now what this means is that we're going to be having 0.9 over 1000. Now if you change this to multiplication, then you switch this over, this will now be 100 cubed. And 100 cubed will give you 1 million. Okay? So you see here, this takes out this. So we are left with 0.9 times 1000, and that will give us 900. And this would be kilogram per meter cubed. 900 kilogram per meter cubed being the density. Now the weight in air would now be, weight of the material in air will be 100 grams. 100 grams is 100 divided by 1000 to bring it to kilogram. Then multiply by 10 meters per second squared to bring it to Newton. And then what we see here is, of course, these two zeros cancel this one cancel this, and we are left with 1 Newton. So the actual weight of the material in air is 1 Newton. Now, let's find the upthrust. The upthrust, therefore, becomes the volume that is, remember, it is volume times density times G. Okay? But in this case, the upthrust becomes 2 over 3 of volume. Volume is 6.67 times 10 raised to the power minus 6. Then multiplied by density, which we have calculated to be 900, multiplied by G, which is 10. So the upthrust force is therefore, now let's look at what we have here. 2 over 3 multiplied by 6.67 times 10 to the power of minus 6. That will give you 4.45 times 10 raised to the power minus 6. Now all of this multiplied by 9,000. Okay? Now what does this give us? Final upthrust is 0.04002. Now this is the upthrust that is felt, and this is in newtons. Now let's find the weight. The weight in water, the weight in the liquid when it is immersed. So the weight in liquid will now be weight in air minus upthrust. And that will give us weight in air is 1 Newton minus 0.04002 Newton. So our final answer here is 0.95998 newtons. You can approximate it to 2 decimal places if you like and say 0.96 newtons. Whichever it is correct. So this is how you apply upthrust to solving problems like this. We have established, according to Archimedes' principle, that when an object is partially or completely immersed in a fluid, the fluid there being either liquid or gas, it experiences an upthrust which is equal to the weight of the fluid displaced. Now that we've established that, we then go on to see different kind of cases for different objects that is partially or completely immersed in fluids. Now, in some cases, you see that the objects themselves will float. That is, they don't sink to the bottom of the fluid. And some will just go right down to the bottom of that fluid. That is, they sink. Now, what determines which objects float and which objects sink? This is what we want to consider in what is known as the principle of flotation. First, let us look at what the principle of flotation is, and then we now look at the conditions that has to be fulfilled for an object to float when immersed in a fluid. So, starting with the principle of flotation, the principle of flotation states that an object will float in a fluid when the upthrust experienced by it from the fluid is equal to its own weight. Let's put that down. An object will float a fluid, or let me use when immersed in a fluid if the upthrust from the fluid it is immersed in is equal to the object's weight. Now, what does this mean? Whenever you take an object and you immerse it into a fluid, the fluid here, note, the fluid is liquid or gas. So when you immerse it into a fluid and it's able to displace enough fluid that equal in weight to the weight of that object itself, that means that the upthrust that is experienced, remember that we said the upthrust experienced is equal to the weight of the fluid displaced. So if that fluid itself gives it an upthrust that is equal to its own weight, then it will float. I mean, think of it like this. We mentioned that upthrust is a cushion effect, right? Now, if the cushion effect it is experiencing is equal to its own weight, that means equilibrium is reached and then it balances at that point. So that is why you see that the object will float, because it is able to displace its own weight in the fluid. However, this is not the only reason why an object will float in a fluid. There are two things we have to consider. Now, conditions for flotation. For flotation, the first thing that will make an object float is the case of density. And how does density affect flotation? You see, when you have an object that is less dense compared to the fluid in which it is immersed, then that object will float. So objects less dense than the fluid will float. Take for example when you have plastic. If you put plastic on water, it floats. Why? Because plastic is less dense than water. The same thing happens to every other material that is less dense. Even liquids as well that are less dense than another liquid will float on top. For example, if you have a petrol or kerosene, they are less dense. When you pour it on water, it will float on the top of that water. This is one of the reasons why objects float when immersed in a fluid. Now, the second reason is the shape of the object. Shape of the object. Now, to explain this, see, back in the days, canoes were made with wood. And it is easy to say that because wood can be less dense than water, then probably that is why canoes float on water. But over the years now, we've seen different types of flotation devices, from ships to the speedboats to different kinds of materials that float on water, even the submarine. And they are made of metals, different type of metals that are more dense than water itself. Yet, when they are on water bodies, they float. Now, this is because of the shape. Now, when you consider the shape of a boat, you see it has a lot of air space within it, and as a result of this, it is able to float on water, because that kind of shape gives it the opportunity to be able to displace its own weight in water. And when it displaces its own weight in water, according to the principle of flotation, then the object will float. So you see, if you have ever watched videos or you've seen physically where the ships are launched into water, you see that the moment they go into the water, they displace a large volume of water. Now, that volume of water, if you are able to collect it and measure the weight, it is equal to the weight of the boat itself. That is why you see that boats will float. This is why you see that ice will float. This is why you see even heavy machinery, submarines and the likes, they will also float. I mean, consider a submarine, for example. Submarine is able to float, and at the same time, it is able to sink in water. Now, this also plays on the principle of flotation. Now, let's consider this to be a submarine, for example. Let's say this is a submarine. It has a shape like this. Then it has this part where the crew and everybody is. But beneath it here, you see what we'll call the air columns. Okay? You see, this part is what actually makes the submarine float. When this place is empty, that is filled with nothing but air, the submarine will float. This will give it the ability to be able to displace its own weight in water. Now, whenever the crew on the submarine wants to submerge the submersible itself, what they do is they let in water into this place. So the moment they open some space here, water will run into it and fill up this space that we have here. The moment water fills this air column, the submarine will be able to sink to the bottom of the ocean, and then it will continue its mission under the water. Then at any point, if they want to come back to the top of the water, all they have to do is run this water out of this air column, and then the submarine will rise above water again. So you see, because of the shape, it is able to displace its own weight in the fluid and follow the principle of flotation and then float. The same thing happens when you're trying to swim. You see, what you are trying to achieve is to be able to displace enough water that is equal to your weight. If you are unable to do this, you won't be able to float on the water. This is why you see some people, when they are at the pool, they relax themselves in some kind of manner so that they are able to displace even more water. And if you're able to achieve it, that you are able to displace water that is enough, that is equal to your own weight, you find yourself floating on water. This is the same thing that happens with things like paper clip. When you put it on water carefully, if you're able to put it on water carefully, it will float, because at that point it displaces its own weight in water. But if you put it awkwardly in water, it doesn't, so it sinks straight to the bottom. All of this plays on the principle of flotation. But what I want you to get from this video is that there are two things that determines whether an object will float in fluid. The first one is the density. If it is more dense than the fluid, it will sink. If it is less dense than the fluid, then it will float. Now, in some cases, when the object is more dense, it is still able to float if it is shaped in such a way that it will help it displace its own weight in the fluid. These are the two conditions that determines whether an object will float or not. Hence, the principle of flotation. I hope you've learned something. If you do have any question, ensure that you put it in the comment section and we'll attend to all of your questions. In our study of Archimedes' principle, the principle of flotation amongst everything, that is equilibrium of bodies in liquid, one word that always keeps coming up is density. And then in some cases, we also talk about relative density. So it's important that we look at what density means. Now, I know from your SS1 days and even in your junior secondary school days, you must have talked about density, and it's often described as the ratio of mass per unit volume of an object. But what does it really mean? What is the physics behind what we know as density? So we'll start by understanding the concept of density. Now, there's this common question that was used as interval trivia question at some point. You will be asked like this. They will ask you something like this. They say, which is heavier? 1 kilogram of stone or 1 kilogram of feathers? Now, that question in itself can throw a lot of people off, because immediately you imagine it, you think of feathers as something that is light. So you think that 1 kilogram of it should be lighter than 1 kilogram of stones. But in reality, it is false, because the mass of both materials is the same, and they should feel the same effect from gravity, because gravitational acceleration is the same at that point. So what you will experience, the effect of the weight when you hold it up, is the same. However, there is a difference. Now, what is the difference? Is that when you have 1 kilogram of feathers compared to 1 kilogram of stone, their sizes are not the same. The size of 1 kilogram of a stone might even fit your palm, depending on the kind of stone you are talking about. Whereas if you want to pack 1 kilogram of feather, you will need a big sack for that. So you see here that what we are actually considering here is not basically just the mass, but the volume as well. So this helps us to understand what density is. To understand density, you need to look at two materials of the same size and look at how heavy they are for what they look like. So when you are considering how heavy something is despite its size, what you are looking at there is density. For example, I'm going to try to draw equal shapes now. Just assume for a moment that these shapes are equal size. And then this is made of polystyrene. You know what polystyrene is, right? That white material that is often used to pack gadgets. Like if you buy a TV or you buy any fragile material you buy that is boxed, you often see that white substance that is used to guard it so that it doesn't get damaged during transportation, right? That is polystyrene. And then the same material, a different material now of the same size. Now let's say this is made of pure gold. I know if I ask you to pick one, you will definitely go for the gold because it is more expensive. But we are not looking at the price now. We are looking at the weight of this material. They are the same size, but which one do you think would be heavier? Of course, the gold would be heavier. Now, they have the same size, yet one is heavier. Why is that so? That is dependent on what? Density. Density. So if you are asked to define density, just think of it. Is that when you have a volume of a substance and it is feeling heavy, and then the same volume of another substance not feeling as heavy as that, it is because one packs more mass into its volume. So that is when you have more mass in a particular volume, then that material is denser, which is why it is heavier. So I like to describe it as how heavy a substance is based on its size, as it's compared to its size. But if you're going to define it, I would like you to define it as the ratio of mass of an object per unit volume. Let's put down that definition. Density is defined as the ratio of the mass of a substance per unit volume. So if you follow this definition, we can then say density, which is denoted with this symbol, equals mass m over volume v. So density equals mass over volume. And this equation can be used in different ways. You can also say that mass equals density times volume. And if you are asked to find volume, volume would then be mass over density. You can always twist the equation depending on what you are looking for. But what do we take away from what we have defined here? Is that when you have two objects of the same volume, one is going to feel heavier than the other because of the amount of mass it packs into its volume. And that is what describes the density of that material. Now that we know what density is, you can define it, you can explain it using examples around you. Then what is the concept of relative density? And why is it important to our study of equilibrium of bodies in liquid? Now, you know density is the ratio of mass per volume, right? Let's pen that here. Density equals mass over volume. So now that we have that pin there, then what is relative density? You see, what relative density seeks to establish is a comparison. It is actually comparing materials with the more common material that we have. We already know that Earth itself is about 70% water. So with our understanding of water, we can describe the densities of other materials. So what relative density does is that it compares the density of any material to the density of water. So it is basically the ratio of the density of the object and the density of water. Let's put that down. Relative density compares the density of an object to the density of water. Now, how we establish this is by saying relative density equals density of object over density of equal volume of water. Now, to make you understand this, when I was trying to explain density earlier, I drew two boxes and I said that the one that feels heavier is the one that packs more mass and as a result is more dense, right? So we look at two objects that have the same volume and then we can tell their density by how much mass they pack into that volume, and then we tell that by how they weigh, right? So if I should get equal volume of water to that of a material and then I compare them together, the volume is the same, but in that case their masses are going to be different just as much as their density are going to be different. So you can compare it by mass and you can also compare it by density. See, that comparison is what we know as relative density. So when we have relative density becoming density of object over density of equal volume of water, we can also say relative density equals mass of object over mass of equal volume of water. Since density is telling us how much mass the object packs into its volume. Now, this is very important because it helps us to tell which object will float in water. Remember, when we talked about the principle of flotation earlier, we did talk about how that one of those conditions for flotation is the density of the material. And just by providence, the density of water is 1 gram per cm cube. Okay? Density of water is 1 gram per cm cube. Okay? Which means it is 1000 kilogram per meter cube. Okay? So, whenever you now take the ratio of the density of a substance to that of water, and then you get a value that is greater than 1. If relative density is greater than 1, then object will sink. Okay? But if relative density is less than 1, object will float. All of this follows the Archimedes principle. So if you are trying to put an object in water and you want to determine if that object will float or if the object will sink, all you need to do is compare the mass of the object to the mass of equal volume of water, or you compare the density of the material to the density of water. So when you do that, you should be able to get what we know as relative density, and if it is greater than 1, the object will sink, and if it is less than 1, the object will float. Now let us do some calculations revolving around density, relative density, principle of flotation, and the Archimedes principle. This is a UTME question of 2024. It says a solid cube of aluminum is 1.5 centimeters on each edge, and the density of aluminum is 2700 kilogram per meter cube. Find the mass of the cube. So this relies on our knowledge of density to solve the mass of this cube. And here's how you solve it. First, note that the volume of the cube would be 1.5 centimeter times 1.5 centimeter times 1.5 centimeter. Basically 1.5 centimeter, all in bracket, then you cube it. But I don't want to work in centimeter because what we have here is in kilogram per meter cube. Now please take note of this. Depending on the question, I believe the way this question was set, you're supposed to solve your answer in grams. So for that one, you have to convert this to gram per cm cube and then calculate this in centimeter like this. But regardless of how the question looks like, you can always solve it and then convert back. So in the case of this question, the way it was set in the JAMB exams, do ensure that you convert this to grams per centimeter. That will be 2.7 gram per centimeter cubed. And then you can just find the volume and then solve the rest. But in this case, I want to show you how to solve it in the proper SI unit, and then I'll show you how to convert it in the end. So when you work with this is basically, if you convert this to meter, you will have 0.015 in brackets. Remember, this is now in meter. Then you cube it. And then what you will get is 3.375 times 10 to the power of negative 3, all in meter cubed now. So this is the value of the volume. Okay? So now when we work with this, we can now try to get the mass. Remember, density equals mass over volume. Now this implies that mass will be what? Density times volume. So the mass of the aluminum cube is now the density of aluminum, which is 2700 kilogram per meter cubed. All of this now multiplied by the volume. The volume is 3.375 times 10 to the power of negative 3 in meter cubed. So easily meter cubed cancel meter cubed. And then when you multiply what we have left here, you will get 9.1 approximately. 9.1 grams. Because your answer is basically 0.0091 and so, but this will be converted to 9.1 grams. That means the answer for this question is 9.1 grams. This question from 2024 UTME says a solid cube of aluminum is 1.5 cm cube on each edge. The density of aluminum is 2,700 kg per meter cube. Find the mass of the cube. Now, to solve questions like this, you can bring them all to SI unit and then solve. But please bear in mind that UTME questions are always multiple choice questions. So as a result, you may have to solve based on the units provided in the options. Now, I have not given the options in this question because I want to show you how to solve it in the proper SI unit first. So we'll solve it using the proper SI unit. However, take note, because of the way the question was set in 2024 UTME, the options provided were all in grams. So for that kind of a question, you will have to convert this one now to grams per cm cube. So, and that will basically give you 2.7 grams per cm cube. And then you can use the remaining step in the calculation to solve and get your answer in grams directly. But I'll be showing you how to solve this in the proper SI unit. So pay attention. Here's what you do first. The first thing you want to do is to convert the length. Length equals 1.5 cm cube. And this is basically divide by 100. That will give you 0.015 meter. So that will mean the volume is 0.015 meter all cubed. And when you compute this, you will get 3.375 times 10 to the power of negative 6 meter cubed. This is the volume of the aluminum cube itself. Now let's find the mass of the cube. Now don't forget that density is mass over volume, and this implies that mass would be density times volume. So let's apply that. The density is 2,700 kilogram per meter cube. Now multiply that by the volume, 3.375 times 10 to the power of negative 6 meter cubed. Now you see meter cube per meter cube is gone. Our answer is going to be in kilograms. So the mass is therefore, when you compute this, you get 9.1 approximately times 10 to the power of negative 3 kilograms. So this is the answer in kilograms. And in order to bring this to grams, you divide it by 1,000. And when you do so, you multiply rather by 1,000. So the same mass will now be 9.1 grams when you bring it to grams. So if you are solving this as the UTME question that it is, based on the options provided, when your options are in grams, you pick the 9.1 grams. But when the options are in kilograms, ensure that it is 9.1 times 10 to the power of negative 3 kilograms. And that's the solution to this question. Let's solve this 1984 question, which says that what volume of alcohol with a density of 8.4 times 10 to the power 2 kilograms per meter cube will have the same mass as 4.2 meter cube of petrol, whose density is 7.2 times 10 to the power of 2 kilograms per meter cube. Now note, it's a UTME question, that is from the JAMB exams of 1984. What do we see in this question that will help us to solve it right? Now, the thing we are seeing here is that they have equal mass. So if the mass are equal, remember that mass itself is what? Density times volume, right? So that is, we have to equate the mass of both substances, that is alcohol and petrol. So therefore, we have density of alcohol multiplied by volume of alcohol equals density of petrol times volume of petrol. And this is what we use to solve it. Okay, so let's interpret this here and then we find our answer at this page here. So what's the density of alcohol? The density of the alcohol we are working with here is 8.4 times 10 to the power of 2 kilograms per meter cubed. Okay, and multiply that by the volume, which we do not know. They said what volume, so we call that V, equals now density of petrol. That's 7.2 times 10 raised to power 2 kilograms per meter cubed. And then we multiply that by the volume, which is 4.2 meter cubed. Now from here, to get this volume would then be this, which is 7.2 times 10 raised to power 2 kilograms per meter cubed multiplied by 4.2 meter cubed, all divided by this density here, which is 8.4 times 10 raised to power 2 kilogram per meter cubed. Now easy, kilogram per meter cube, kilogram per meter cube, that cancel out. 10 to the power of 2, 10 to the power of 2, that cancels out as well. Okay, now 4.2 here 1, 4.2 here is 2. So the volume is 7.2 divided by 2. Okay, and we have the unit in meter cubed. Now let's solve. 2 goes in 7, 3 times, remainder 1. So point, 2 in 12, that is 6. So that's 3.6 meter cubed. That means the correct option that you will go for in this question is what we see in option B. So our answer would be option B. Here is another question you can practice with. It's from the 2018 UTME question. Please feel free, pause the video, try it out yourself, and then you compare your solution and your method with what is used at the end of this video. Now, in this question, we see that the density of 400 cm cube of palm oil was 0.9 grams per cm cube. That's before frying. Now, if the density of oil is now 0.6 grams per cm cube after frying, assuming that no oil is lost due to spilling, the new volume will then be, so we have to find the new volume given that no oil is spilled but the density dropped. What will happen to the new volume? Let's find that out. So don't forget, you compare this with what you have gotten so that we see how well you can solve questions like this. So as usual, since no oil is lost, the mass remains the same. So equate the mass before frying to mass after frying. Mass before frying equals mass after frying. Okay, so what is the mass before frying? That is the product of volume and density. So the volume is 400 cm cubed times the density is 0.9 grams per cm cube. Now you may be wondering, why have I not converted this to the SI unit? If you look at all the parameters provided here, that is the variables rather provided in this question, we see here in cm cube, grams per cm cube, grams per cm cube. So we can easily solve and get our answer in grams. As easy as that. Since we are trying to solve for the volume rather, we should be getting an answer in cm cube, because gram per cm cube will cancel grams per cm cube and we'll be left with cm cube as our answer. So it's quite easy. I don't need to convert, except if you look at the options provided in questions like this and what you have there have a different unit entirely, then you may need to convert to such units that you have in your options. So let's continue. Now this equals, now on the other side, mass after frying will be the volume, which you do not know, multiplied by the density after frying, that's 0.6 grams per cm cube. Now make this volume the subject. V therefore becomes 400 cm cube times 0.9 grams per cm cube, all divided by 0.6 grams per cm cube. Now grams per cm cube, grams per cm cube. 0.6 here, 3 can go. This will be 2. This one here is 3, right? This gives you a fraction of 3/2. Okay, so what we have here now, we can now break it further and say 2 here 1, 2 here 200. So we have 200 cm cube multiplied by 3, and our answer is therefore 600 cm cube. So that is, if no mass is lost, the volume is going to increase after frying. So this is the solution to the question. If you did get the same thing, put it in the comment section. This question from the 2020 UTME says, a solid weighs 4.8 grams in air and 2.8 grams in water, and then 3.2 grams in kerosene. Now the ratio of the density of the solid to that of kerosene is, so in order to get this, we have to consider the relative density of the solid, the relative density of kerosene as well. So let's start by finding the relative density of the solid. Now we say relative density of the solid will be the weight in air over weight of equal volume of water. Another way to put this is weight in air over upthrust. Remember that the upthrust is the weight of liquid displaced, right? And that is the equal volume of water that is displaced. You find the weight of that volume. So let's apply that. So what we now have here will be the weight in air is given in the question as 4.8 grams. Now the upthrust experience is 4.8 grams minus the weight in water, which is 2.8 grams. This will give you 4.8 grams divided by 2 grams. So, and it does not have a unit, so the relative density of the solid is therefore, when you divide this will give you 2.4. 2.4. So that's the relative density of the solid. Now let's find the relative density of kerosene. Now for the relative density of kerosene, we'll find the weight, that is upthrust in kerosene, over upthrust in water. Okay, so when we apply this, what do we have? What's the upthrust in kerosene? That is 4.8 minus 3.2 divided by the upthrust in water. We've already done that. 4.8 minus 2.8, that gave us 2. Now when you solve this would give you, here we are going to be having 8 minus 2, that's 6. 4 minus 3, that's 1. So 1.6 over 2. So the relative density in kerosene is therefore 0.8. No unit as well. But the question says the ratio of the density of the solid to that of kerosene. And that will be the ratio now would be density of the solid, that is 2.4, divided by density of kerosene, 0.8. Relative density in this case. Now this can be solved by saying 24 divided by 8, and that will give us 3. So the ratio here is 3. Now let us consider how you can measure the density and relative density of different materials. Now the first material we're going to start with is objects that sink in water. So objects that sink in water. Now this means that the densities of this object is greater than that of water. So as a result, they are going to sink. So how can you determine or measure the density and even relative density of such materials. Now, I'm going to divide this into two. We'll start first with density of regular solids. Okay, so when you have a regular solid and you want to find the density or even the relative density, how do you go about this? Now, the first thing you need is the mass. Measure the mass, and you can do this using electronic scale or the beam balance. Electronic scale or beam balance. Now, these are instruments you can find in a physics lab. All you need to do is place the object on the electronic scale, and then you measure the mass of that object. And then if you are using a beam balance and you compare the mass of the object to known masses, you start adding masses to the beam balance, and that way until it balances. The moment it is level, it means that the mass on the left equals the mass on the right. So that way you get the mass of the object you are trying to find its density. Now, once you have the density, the next thing you need is to measure the volume. Measure the volume. Now, as you can see here, I have said we are using regular solid. Okay, so if it is a solid that is a cube, for example, you just have to multiply the length by itself 3 times, because the volume of a cube is length times length times length. If it's a cuboid, you do length times breadth times height. If it is a sphere, you do 4/3 pi r cubed. If it is a cylinder, use all the equations that you use to measure the volume of such regular solid. Now, this would would depend on your knowledge of geometry. So you have to understand how to get the equations for volume of the different shapes you are working with. So depending on the shape, that is what will determine the kind of equation you use to derive the volume of such material. Now, if you are able to measure the mass and then you are able to measure the volume, the next step is to find the density. Don't forget that density will then be what? Mass over volume. Now, for example, now if you are dealing with a cuboid, right, and then you measure the mass, let's assume that you get the mass to be, say, 100 grams. The mass is 100 grams. Now, the next thing you need is to find the volume. Now, let's say that for the volume, let's assume that the length is 2, the breadth is 5, and then the height is 1. Now, you see, 2 times 5 times 1 will give you 10. Now, in that case, when you do 100 divided by 10, you get 10 grams per cm cube, because we are working in cm cube in this case. So once you have the volume like that, and then you have the mass, you have gotten the volume by just doing mass over volume. I hope you understand this process now. So once you have the density, of course, you can also then find the relative density. Don't forget, the relative density is now what? Either you use mass of solid over mass of equal volume of water, or you say density of solid over density of water. Either of these two equations can help you get the relative density of such solid. Now, this is for the case of regular solids. Don't forget, you need mass and volume. Then you apply mass over volume to get density, and then you do density over density of water to get the relative density. Don't forget that density of water is 1 gram per cm cube, or 1000 kilogram per meter cube. Now, what if the solid you are dealing with is irregular? Irregular solid. Now, if you are dealing with an irregular solid, you can easily get the mass. You can still get the mass using the electronic scale or beam balance. Where you are going to have issue is the volume. So to get the volume, you have to do that by an experiment. Now, this is what you do. To get the volume, okay, you are going to get a measuring cylinder that solid will fit into. Now, if the solid is big and cannot fit into a measuring cylinder, you can use a Eureka can. Now, let me explain how both of them work. In the case of a measuring cylinder, it looks something like this. Now, fill it to a level with water and mark the level it gets to. Okay? Now, you dip the solid into the water and that will cause the water level to rise. Okay? Because the moment you dip it into it, it will displace some of the liquid. So as a result, the water rises. You see this change here? This here indicates the volume of the solid. You see the difference here is how you get the volume of that solid. And if it's such a big material that cannot fit into a measuring cylinder, this is what a Eureka can looks like. It has an outlet like this. So you then place a measuring cylinder at this outlet. Make sure it's empty. Now you fill this Eureka can with water until it gets to this level. Basically, allow the water to pour out first. So when it pours out, you leave it until nothing is dripping out again. Then you, whatever pours here, throw it away. Then put a fresh measuring cylinder at this point. Now dip the solid into the Eureka can. It will cause the water level to rise. So that will make more water to spill into this measuring cylinder. Now once it stops spilling, whatever volume of water you now get in this determines the volume of the solid. And what is next is you just apply density equals the mass you have measured over the volume you get from doing this simple experiment. And just like we did here, you then go on to do mass of the solid over mass of equal volume of water, or you do the density of the solid, which you get from this equation, over the density of water, which is 1 gram per cm cube or 1000 kilogram per meter cube. Once you compute that, you get the relative density of that irregular solid. So by following these simple steps and procedures, you can get the density of whether it's a regular solid or an irregular solid. Please, if you do have any question on this method, ensure that you put it in the comment section and we'll always attend to all of your comments. Now let's learn how to measure the density and relative density of solids that float on water. Now, if you are trying to get the density of an object that will float on water, there's a simple experiment that can help you determine that. Now, let me describe the experiment and then we use what we get from the experiment to deduce the density. So the first thing you want to do, now because the object will not sink in water, we use another object that will sink in water in this experiment, and that object that we are using is called a sinker. Okay, so you need sinker. Another thing you need is a thread. Another thing you need is a spring balance. Now the spring balance is an instrument used to measure weight, and then of course you need the object. Then you need water in a container. So what you now do is, the first thing you do is you put some water into a container and then you put your spring balance, tie a thread to your spring balance. Now let's assume the water gets to this level, and then you immerse the sinker. This is the sinker now. Immerse the sinker in the water and then measure the weight. You measure the weight of the sinker when it is completely immersed in water. Okay? Measure weight of sinker completely immersed in water. Immersed in water. So let's call that W1. Okay? Now, for sake of space, I won't be giving you more of diagrams like that, but I'll explain what is happening. Now, for step 2, you measure weight of sinker in water plus the object in air. Now this one I'm going to describe with a diagram, so pay attention here. We have the spring balance connected into the sinker. Now the sinker is here in the water. Then we attach the object you're trying to measure its density here. This is the object and this is the sinker. So you see here, the sinker is still in the water like in this case, but the object is added to it. So what will happen is that the weight comes down a little bit now from what we have before. Okay, so this would give us the weight known as W2. Okay, this is W1. Now the third step will now be measure weight of sinker plus object completely immersed in water. Okay, that is at that point, let me also add a diagram for that just to make it easy to understand. Now the object and the sinker are both immersed, and then you will see that the weight measured will actually reduce from the initial one we have here. So you see the weight is at this point here. When we added the object, it is now at this point. By the time we added we immersed everything in the water, it goes up a little bit from where it is here now, and this will give us W3. Okay, so now with all these three that we've gotten, this is now how you will get the density of the material. The relative density would then be weight in air over upthrust. And how do we get this? What is the weight in air? The weight in air is actually W2 minus W1. Let me analyze that. Remember, at this point, we have just the weight of the sinker when it is immersed. And here we have the sinker immersed, which is W1 initially, plus the weight in air. So W2 is actually the weight in air plus the weight of sinker immersed. So by the time you remove the weight of sinker immersed, what you are left with is what? The weight in air. That's how we get the weight in air, W2 minus W1. Now, divided by the upthrust will be that cushion effect you feel when everything is now completely immersed. And that is W3 minus W. Now, remember now, we have to remove the weight of sinker and whatever you feel left. You know that what is here now? This is supposed to be W2 rather minus W3. W2 minus W3. Let me explain how that is. This is heavier. because it is not yet feeling that cushion effect. The moment the cushion effect comes in, it feels a bit lighter. So it's that difference we need. So the difference between these two weights gives us the upthrust. That's why it's W2 minus W3. And that is how you get the relative density of a material that floats on water. Now, if you need to get the density, you can always relate this with the equation. Remember, the relative density of a material equals the density over density of water. Right? So once you've gotten the relative density from this, you just plug it into this equation here. You already know the density of water is 1 gram per cm cube or 1000 kilogram per meter cube. So that is the density of the material is therefore relative density times density of water. So whenever you have the relative density of a material, you can apply this equation to get the actual density of that material. So let me recap. The first step, measure the weight of the sinker when it is completely immersed. Then the next step, you measure the weight of the sinker when it is immersed in water plus the object still in air. Like as you have here, you label that one W2. And then you measure the weight when everything is completely immersed in water. That way you'll be able to get the upthrust by finding the difference between W2 and W3. So the relative density is therefore W2 minus W1 over W2 minus W3. That gives you relative density. And then the actual density is then the relative density multiplied by the density of water, which is a constant at 1.0 grams per cm cube or 1000 kilograms per meter cube. Now that you know how to find densities and relative densities of a solid that will sink in water, a solid that will float in water, and even densities of regular and irregular solids in both cases, let us now look at how you can find the density of a solid that is in particle form or powder form. Relative density of solid in form of particles or flour or powder rather, or powder. Okay, so like for example, I'll be using sand to explain how you can do this. So you see that sand is in particle form. How can you find the relative density of sand? First, let's list the materials you need for this. Materials required. You need a density bottle. Secondly, you need electronic scale or chemical balance. Thirdly, you need water. Distilled water is the best in this case. And then you need sand or whatever particle you want to find the relative density of. Now, this process is dependent on the fact that relative density is the mass of the substance divided by the mass of equal volume of water. Now, how do you get these measurements that will help you determine the relative density of sand in this case? Now, here's step 1. Measure the mass of empty density bottle. Measure the mass of the empty density bottle. And then we denote it M1. So you take the density bottle, make sure you clean it, Ensure that there is no particles inside, there is no water, nothing. Clean it and then put it on your chemical balance or your electronic scale, and then take note of the mass and label that M1. You can record it as M1. Now, once you've done that, you then go to step 2. Pour some sand into the bottle and measure the mass. Now we are going to record this as M2. Now what you are doing here is that you take some of those the sand you want to measure the relative density of. You pour it into the density bottle. Make sure you don't fill up the density bottle. It is advised you do it to either 2/3 of the bottle itself. Make sure there's still some space in the bottle. Then once you've done that, you then measure the new mass. Remember that the mass you are getting here is now the mass of the density bottle plus sand. So let's note that here, that this M2 is mass of bottle plus sand. Okay? Now we go to step 3. Fill the bottle with water and measure mass of bottle plus sand plus water. Now, you see that you have only filled it to like 2/3, then you add water until the entire bottle is full, and then you measure the mass. Now we're going to call this M3. This is mass of bottle plus sand plus water. And then we go to step 4. Now step 4 is measure mass of bottle filled with water only, and then we call this M4. Now you can now pour out everything and then clean the bottle again, and this time fill it with only water and then measure the mass and record that as M4. Now note that relative density is supposed to be mass of sand over mass of equal volume of water, right? So what you can do to get all of this is to apply this equation. RD, which is relative density, becomes the mass of sand. How can we get the mass of sand only? The mass of sand only would be M2 minus M1. That is, we subtract the mass of the bottle from mass of bottle plus sand over. Now, how do we get the mass of equal volume of water? Remember that in step 3, we have water plus sand plus bottle. But in step 4, we have mass of bottle plus water alone. Now, what you need to do is to apply M4 minus M1. And then minus M3 minus M2. This way you are going to get the mass of equal volume of water. So as long as you follow these steps and you record the values M1, M2, M3 and M4 as indicated in the steps, by applying this equation, you will get the relative density of sand. And of course, if you now need the density, all you need to recall is that density itself will now be, remember that relative density is density of the material divided by density of water, right? So it will now be relative density multiplied by density of water. And with these equations, you can get the relative density of sand or any other solid in particle form or powder form, as well as the relative density. So density and relative density. By following the methods discussed earlier, you can find the relative density of sand. But what if the particle you're trying to find its relative density is soluble in water? If you apply the same method, your result is going to be off what is required, because as it dissolves, it changes the result. So you will need to do the same process. However, this time, instead of using water, you would use a particular solution known as turpentine. Right? Now, you see, turpentine is a particular liquid that is immiscible with water. And at the same time, materials that will dissolve in water do not dissolve in turpentine. But you have to be careful when doing this experiment, because it is volatile and it can also affect you. So please, if you are doing something like this, be very careful. Ensure you are doing it in the presence of a teacher who will guide you to do the experiment safely. Now, what we are doing now is measuring the relative density of materials soluble in water. So, relative density of solids soluble in water. Now, the steps. I'm recapping these steps so that you do not mix it up. First thing is measure mass of density bottle. Bottle only. And then we call this as M1. So make sure that the density bottle is empty. Clean it, make sure there's no particle, no water, nothing on it. Just the bottle alone. And then you record it as M1. Step 2. Measure mass of bottle plus solid. Ensure that you don't fill it to the brim. And then we call this M2. Don't fill it up. Make sure there's still some space in the bottle. And then measure it and record your value as M2. Then step 3. Step 3 would be measure mass of bottle plus solid plus turpentine. This time you fill the bottle to the brim, and then we record this as M3. So now the bottle is full of the solid that is soluble in water plus turpentine, and then we record our value as M3. Now step 4. Measure mass of bottle plus turpentine only, and then we call this M4. That is, to an empty bottle, you fill it up with turpentine to the brim and measure the mass using your chemical balance or your electronic scale. Now, once you've gotten M1, M2, M3, and M4, you then get your relative density by applying this formula. M2 minus M1, and then multiplied by density of turpentine, all divided by M4 minus M1 minus M3 minus M2. Now, once you apply this equation, you will get the relative density of that material. Now, note, the density of turpentine is 0.86 grams per cm cube, which is 860 kilogram per meter cube. So when you apply these steps, you should be able to find the relative density of solids that are soluble in water. Once again, if you are doing something like this, be very careful. Ensure you do it in the presence of a skilled personnel, a teacher preferably, so that they will guide you to do this experiment safely. And please, if you are not yet subscribed to the channel, take a moment now to click the subscribe button and hit the notification bell icon. We still have more coming your way. Let's go. Now let's learn how to find the relative density of a liquid. Relative density of liquids. Now for this, the materials you need are as follows. Materials required: density bottle, number 2, you need the electronic scale or chemical balance. Number 3, you need water. Number 4, you need the liquid. Now, here are the steps you follow to get the relative density of the liquid. Step 1. Measure the mass of an empty density bottle. Now we call that M1. Now to do this, make sure you clean the density bottle, dry it properly before you then measure the mass. And you do that by using the electronic scale or chemical balance. Now step 2. Measure mass of bottle plus liquid. That is, you fill that empty density bottle now with the liquid you are trying to find its relative density. Make sure you fill it to the brim and then measure the mass. You then record that as M2. Step 3. Measure mass of bottle plus water. Now what this means is that you then take a new empty density bottle, or if you are using the same one, you make sure that you pour out the liquid completely, clean it again and dry it, ensure that there's nothing inside. Then you now fill it this time with just water to the brim and then measure the mass, which you are going to record as M3. Now the relative density of that liquid will now be done by this equation. Remember, it is mass of the liquid over mass of equal volume of water. So the mass of the liquid, over mass of equal volume of water. Now to achieve this, you apply this equation. To get the mass of the liquid alone, you're going to do M2 minus M1. And to get the mass of equal volume of water, you're going to do M3 minus M1. Now by applying this equation, you get the relative density of the liquid. Don't forget, if you have any question, we are always here for you. Remember, we are your flawless school too. So if you have any question on what we are doing so far, please put them in the comment section and we'll attend to all of your comments. Finally, on equilibrium of bodies in liquid, we have to consider the hydrometer. Now the hydrometer here is an instrument. It is used to measure the relative density of liquid. Now it's a common question you will find in multiple choice question, that which of the following can be used to measure the relative density of a liquid, and the answer to that is the hydrometer. So let's note it down. The hydrometer is an instrument used to measure relative density of liquids. Okay, now what it looks like is you're going to see a narrow stem, a narrow graduated stem. Graduated means there is markings on it like this to tell you the relative density of the material. Then it has a bulb like this, and then the rest move like this. It looks something similar to this. The bulb is not this big, sometimes it can be very small, but it's larger than the stem itself. Now how it works is that you have to first gently drop it vertically into the liquid. That's the first thing you want to do. Now you take it by the stem and drop it into the liquid. Now the next thing is, if it sinks deep, the liquid is less dense. Then in denser liquids, it floats. Okay, so now this is the thing. Let's assume you have a bowl of liquid or a beaker filled with a particular liquid, and then you drop the hydrometer into it. What will happen is that if the liquid is more dense, the more dense the liquid is, the more it will float. And then the less dense it is, the more it will sink. Now, to be able to read off the actual relative density, that's the fourth thing I'll write here. You can read the relative density from the value marked on the stem. So it's quite easy to use. You just pick it up, drop it gently into the liquid, and then watch whether it floats or sink. Now, at the point where it gets into the liquid, look at it. Let's assume when you put it in a liquid like this now, it then gets to this point, the liquid gets to this point. I will read off the value that is here. Now, whatever value is at this point is what will tell me the relative density of the liquid. Now, here's the thing. If you put it into pure water, what will happen is that the marking you see here is 1.0 because it is graduated in grams per cm cube. So you see it at 1.0. Now, if it is less dense than water, it will sink more. What you have at this point, it comes from 0.1 and on like that until you get to 1. And then from 1, you start saying 1.1, 1.2, 1.3, and so on like that. So in water, it will be 1.0 exactly. If it's in a liquid that is less dense than water, it will sink deeper and start seeing values like 0.9, 0.8, 0.7, and so on like that. But if it is in liquid that is more dense than water, it will then float a little more. You start seeing things like 1.1, 1.2, and so on. That is how the hydrometer works. And please do not mix this up with another instrument known as hygrometer. Hygrometer and hydrometer are not the same thing. Hydrometer is for relative density. Hygrometer is for relative humidity. They are two different things, even though they both start with relative. So it can be a little bit confusing. So sometimes you see both of them in the option and then you don't know which one to pick. Know now that hydrometer is for relative density, while hygrometer will be relative humidity. By the time we start discussing humidity, we'll talk more on the hygrometer, right? But for now, this is what the hydrometer is used to do. So now we've been able to look at equilibrium of bodies in liquid. We can state the Archimedes principle. We can also state the principle of flotation. To recap, remember the Archimedes principle states that when an object is partially or completely immersed in a fluid, it will experience an upthrust which is equal to the weight of the liquid displaced. And then when we talk about the principle of flotation, it says that an object will float in liquid or in a fluid generally if it is able to displace that liquid that is equal to its own weight. If it displaces a liquid that is equal to its own weight, then it will float in that liquid. It could also be a gas. That's why it is often replaced with the word fluid. We've also learned how to calculate density and relative density for different kind of material, and how to use an hydrometer to measure the relative density of a liquid. Now, if you have any question at all on the topic, please drop it in the comment section. But I would advise that you practice with even more questions from the wide past questions, the jam past question, or any other questions that you can find around you. And if you come across any challenging one that you would like some help with, kindly drop it in the comment section and we'll definitely attend to all of your questions. And don't forget to subscribe to the channel. You can do this by clicking the subscribe button, and then help us to share our videos so that we can reach many more students like you who need helpful videos like this by clicking the share button. Thank you so much for following the video so far. We have many more to come your way which you do not want to miss. I'll be seeing you in the next video. Bye for now.